Welcome to Math Mornings. I've missed seeing all of you in person at our lectures in New Haven, but since we're all stuck at home and we at Yale have been learning how to do online lecturing, I thought I would tell you a little bit about some of my favorite mathematics in a short video. While I have this on the screen, let me point out that there's lots of really good math content online, and so you can all find this, I think, on your own, but I can put the links in the comments below the video. 3 Blue, 1 Brown does excellent lectures with wonderful graphics. Mathologer does wonderful stuff, and the Art of Problem Solving has lots and lots of material if you want to learn extra topics in more depth. Okay, so let us begin. The theorem I want to tell you about is called Gauss's theorem on spherical triangles. And I'm just going to state it now, and then I'll explain all the terms as we go. So here you see the sphere and a triangle on the sphere. The triangle has 3 angles. I call them alpha, beta, and gamma. Those are just these Greek letters. And the theorem says that in a unit sphere, the angle sum of the triangle, the sum of the 3 angles, is more than pi, and the difference, alpha plus beta plus gamma minus pi, is equal to the area of the triangle. I think you should find this a little bit surprising if you're familiar with triangles on the regular flat plane. And so we will come back to the theorem to the statement of this theorem in a little bit. But let me first go back and explain what all these words mean. So let's start just with what pi means and what are angles. So over here on the picture, I have a circle and I have an angle, which is a pair of rays, from the center of the circle out. And this little angle between the rays, the way I decide how big it is, this is the common thing that mathematicians do, is I look at the arc of the circle that sits inside this angle, and I measure its length. And the length of that arc is my measure of how big the angle is. That's called sometimes radian measure, but we just think of it as the measure of the angle. And how big can it be? Well, if the circle has radius 1, you could think of it as 1 foot or 1 meter, then we know that if you go halfway around the circle from here all the way to here, exactly to the other side, that length, if you measure it fairly carefully, you'll see it's about 3. And if you get a much better ruler, then you'll see it's about 3.1. And if you get even more precise, you'll see it's 3.14. And you can keep getting better and better estimates of the length. And the number that you get is the number that we call pi. So that's all that pi is. It's just a name for that particular number, which is always the distance halfway around a circle for a circle of radius 1. Okay. On the other hand, well, let me draw another circle here just for just have another picture. If I have an angle which is a right angle like this, then the amount of length over here should be a quarter of the way around, or it's half of what we had before. So this should be pi over 2, right? Which is roughly 1.5 something, 1.57, and so on. And for any angle, you can figure out how to measure the length of the arc that it subtends. It's called the arc inside the angle has a length, and that's how we measure how big the angle is. If it went all the way around, that would be 2 pi, and the full circumference of the circle is 2 pi if it has radius 1. Okay, so that's what we mean by pi, and that's how we measure the angle between 2 lines. Okay, now what about triangles? Well, a triangle in the regular flat plane that we all know, the plane of the screen, is just made by taking 3 lines and finding this region in between the 3 lines, which I'm outlining here in red. That's called a triangle. It's just got 3 meeting points of the lines in 3 pairs, and it has angles, which are these little angles between the lines as they approach the vertices of the triangle. And the sum, and this is a well-known theorem in regular geometry, the geometry that I think all of you have seen little bits of at least, is that the sum of these angles, let's call them alpha, beta, and gamma. I hope you don't mind that I use Greek letters for the sizes of angles. That's just how we often do it. There's no rule about it. Alpha plus beta plus gamma is always equal exactly to pi, which is to say that the sum of the angles is the same as that angle that we drew before that goes halfway around the circle. And I thought maybe we should actually prove this standard Euclidean theorem. Let me draw another copy of these. Let me pull this a little bit. I'll draw another triangle for you, and we'll try to prove this theorem. So here's another triangle, and I'm going to show that these three angles add up to pi. This is something that Euclid knew 2,000 or more years ago. So here's how the proof works. You go over here to this point that's not on the green point I just made. That's the kind of opposite from beta and alpha. This is the point along gamma. And you draw a line. Let me try to see if I can get a good version of this line, which is parallel. So this line and this line over here, the green line and the red line over here, they're parallel lines. And one of the things that you prove in geometry pretty early on is that if you have two parallel lines and another line connecting them, then there are various angles that have to be the same. So for example, this angle beta over here, it has to be the same as this angle over there, because I have a line over here that meets two parallel lines. It's going to meet them in the same way, and therefore the two angles are the same. So beta is also this angle here. And similarly, this diagonal line passing through alpha meets the two parallel lines in the same way. And so alpha over here and alpha over here are the same. And now you see, let me get a red thing again, that over here, the green line, if I go around the green line here, I get an angle which starts over here and goes exactly to the other side of the line. So it must be pi. It's called a straight angle. It's a pi amount of angle. And it's equal to the sum of alpha plus beta plus gamma, I guess in the other order. So alpha plus beta plus gamma here must be halfway around the circle, or pi. Okay, so that's the Euclidean geometry proof, the proof in the flat plane. The sum of the angles is equal to pi. And it's worth noting that in this case, the sum of the angles has nothing to do with the area of the triangle. I could have taken this triangle and made it, in fact, let me just do it since I have a fancy iPad here. I could take this and make it bigger, and I don't change the angles, right? You see that? I made it much bigger and I didn't change the angle. I can make it much smaller and I don't change the angles. So the angles in the area are not related. Okay, now what about the sphere? Here's a copy of the sphere. So the sphere, this is going to be the unit sphere. So it's got radius 1. If I draw the center of the sphere down inside in the middle here, and I draw an arrow, from the center out to the surface of the sphere, I can draw it here, I can draw it all the way to the edge of the picture, I can draw one that comes very close to you, and here's one that comes straight pointing almost at us. All of these in 3 dimensions, all of these lines have length 1. So this is the sphere of radius 1. That's what we mean by unit sphere. And in this sphere, I want to think about its geometry. So I have to tell you what are lines and what are triangles. So what is a line in the sphere? Well, a line is what's called a great circle. What is a great circle? A great circle, I can say 2 things about it. It's the biggest circle you can draw inside that unit sphere, the biggest size circle you could possibly draw. And because you can draw a lot of little ones, of course. It's also the same as the intersection of the sphere with a plane passing through the center of the sphere. So let me draw a picture so you see what I'm talking about. In this picture, if you imagine that this is the North Pole and this is the South Pole of the Earth, then the equator is a great circle. So here is the equator going around the sphere, okay? That is a great circle. That's one of the things we call a straight line in the sphere. Another one is if you draw one of the longitude lines of the globe over here, like that, that's also a great circle. But there's lots of other great circles. Here's another one. There's one I can draw maybe over here. If I draw it well, then it'll be a great circle. I'm not sure I got a very good version of it. And the thing that makes it a great circle is that you get it by drawing a plane. Here's a plane in space, right? Which passes through the center of the circle. And when that plane intersects the sphere, it does so in a great circle. If I draw a plane over here, okay, see that plane? That plane intersects the sphere in this great circle. So that's, and I only choose planes that pass through the center. If I choose a plane that just barely meets the sphere over here and cuts it in a little bitty circle, that's not a great circle. That's just a little circle. Okay, so I don't take those. I only take the planes that pass through the center of the sphere. Those are my great circles, and that's how I make what I call lines in the sphere. And I already see some triangles in this picture. In fact, maybe I'll over here. You see over here where those three red great circles that I drew before, where they meet, they make a triangle. So that's the triangle I'm talking about. Okay, so that's the beginning of understanding the sphere. The second question is, what about area in the sphere? Because we're interested in area. So I'm not going to define for you what surface area means. I hope everyone has some notion of what area should mean. If you needed to paint a portion of the sphere with paint, the area tells you how much paint to use. So that's roughly what area means. Here are some things we know about area. If you have a disk in the plane of radius r, just a regular disk in the plane, then this is a great theorem in mathematics, that the area of that disk is equal to pi times the square of the radius. And the thing that and I'm not going to talk about that today. That's also an interesting fact. The thing that we are going to use today is that the area of a sphere of radius r is exactly 4 pi times the radius squared. Okay, so that 4 I'm not going to explain today. If you want a really good explanation, you should go see one of the videos of 3 Blue, 1 Brown does a really beautiful job of explaining where this 4 pi comes from. Okay, now I should say it doesn't really matter that it's exactly 4 pi for our purposes. If it happened to be a different number, we would get a theorem in which there was a slightly different proportionality constant. So if you're worried that this theorem depends too much on some kind of accident, you shouldn't worry about that. That's just a question of choosing the right units to describe the theorem. So in our case, in particular, we have a radius 1 sphere, and so the area is exactly 4 pi, which is roughly 12 and a half. So that's, we're going to use that at some point in a little bit. That's the number that gives us the total surface area of the sphere. Okay, so now we're ready to think about our theorem. So let's look at the theorem again. So Gauss' theorem states that if you draw one of these triangles, so here we have a triangle like before, but now its sides are arcs of great circles. And the theorem is that the angle sum, alpha plus beta plus gamma, not only is it not equal to pi, it's always more than pi, strictly more than pi. And the difference between them, alpha plus beta plus gamma minus pi, is exactly the area of the triangle. Okay, that's the theorem. So now I think we understand what all the words mean in the theorem. Let's try to think about how we would prove it. Oh, and before we prove the theorem, let's look at an example. So here's an example of a triangle where we can easily see that the theorem is true. So what have I drawn here? This is the sphere in blue, and you see 3 planes cutting the sphere. These are meant to be, if I drew them well, 3 orthogonal planes. So these are planes that meet at right angles. If you look at the way the yellow and the orange plane meet, it's a right angle there. The purple and the yellow meet in a right angle, and there's one more right angle here. The purple and the red, the orange, meet at a right angle also. And therefore, the 3 arcs, the 3 great circles that they generate on the blue sphere also meet at right angles. And you can sort of see right here, I've drawn the triangle that they make. And that triangle has 3 right angles. So that's why I call it an all right triangle. And so in this case, the sum of the angles is pi over 2 plus pi over 2 plus pi over 2. And if I subtract away the pi that the theorem tells me to subtract, I get pi over 2. Everybody can do that little piece of arithmetic, I hope. So pi over 2 should be the area of this triangle. But we can see that that's the area of the triangle just by thinking about the symmetry of this picture. There are really 8 equal triangles in this picture. 8 equal triangles that subdivide the sphere into 8 equal pieces. Namely, we're looking kind of at the front of this picture, but over here in the back, there's another triangle that has the same exact shape as the one we drew. And in this area, there's another one. And similarly, there's one all the way in the back that you really can't see very well. And similarly, the planes have cut the sphere up into another triangle on this side and another here, and so on. So there are 8 triangles. So the area should be 1/8 of the full area of the sphere, which is 4 pi, and that's also pi over 2. So here we have checked that the theorem is correct using an all right triangle. Okay, now it's time to think a little more generally about the theorem. So it's really 2 steps. The first step is to think about what I'm going to call loons. So what is a loon? A loon, if you take 2 great circles, here I drew in this picture, I have 2 great circles that meet, and they meet in these 2 points. And if you think about how great circles have to meet, they have to meet in 2 opposite points. So these are opposite points. Why are they opposite? Well, think about how the planes meet. If the 2 circles are really the intersections of 2 planes, the 2 planes meet in a line, and that line passes through these 2 opposite points. One of them is in the front of the sphere in this case, and one of them is in the back of the sphere. Okay, so, and then these shapes over here between the 2 circles, that's what I call a loon. There's 2 of them, right? This is kind of a symmetric picture, one in the front and one mostly in the back. And these are 2 loons. So I'll call this a double loon because there's 2 of them. And I'm going to ask you, what's the area of a double loon if I know the angle between its great circles? So if the angle is alpha, what is the area? Well, let's see. It should be, let me write it down, proportional to alpha. And this is just common sense, I hope, but it's because if I, for example, if I have alpha and I take another copy of the same thing, just kind of rotated by alpha, it would look like this. Here's another loon, also of size alpha, right next to it. So they add up together to make a loon of angle 2 alpha, and it should have twice the area. And if I put 3 together, it should be 3 times the area. So when I multiply the angle by anything, I should multiply the area by the same thing. So that's what I mean by saying that it should be proportional to alpha. And I know that, and then, so now all I have to do is figure out what's one example that I actually know, and then I'll just know what it is all the time. And the easiest example is to take the example when alpha equals pi. If you think about alpha equals pi, that means that you've started over here with 1 great circle, and you've rotated all the way by pi to get the second circle is the same circle again, and the loon is the entire hemisphere between them, and the other loon is on the other side. So in that case, it fills up the whole sphere, and the area should be 4 pi. And so therefore, the proportionality constant is 4. And so the area in general should be 4 times alpha. Okay, so a double loon is area 4 times alpha. If you'd like, you might want to check this on a slightly less strange example. You could take, let me leave this as an exercise, but you could take a loon with 2 orthogonal great circles when alpha is pi over 2. Okay, then it's maybe easier to see that that this produces exactly half of the area of the sphere, and you can get the same proportionality constant from that. Okay, so now we know that the area of a loon of angle alpha is 4 alpha. Okay, the last part of the proof is just to think about what triangles have to do with loons. And so in this picture, I've drawn 3 great circles. They meet in such a way that they produce, like before, a triangle. And well, they produce several triangles here, but I'm going to focus on this one over here. Let me do it maybe in yellow. Over here, this triangle right there that you see in yellow, in the front of the sphere, that's a meeting triangle. It's made by the gray, blue, and red great circles. If you let me point out that there's another triangle, just exactly the same shape but opposite on the other side. Here's a triangle in the back. You see this triangle, right? And just the symmetry of the operation. A great circle is kind of symmetric through the center, and all the great circles are symmetric through the center. So anything you draw, there should be a front version and a back version, one on the other side. So first of all, the area of the triangle that I'm interested in is this yellow triangle appears twice in the picture. That's one thing to notice. And then the other thing to notice, use a different color maybe, is that we have these three double loons in this picture. So let me start maybe with, let's look at this vertex of the triangle, and notice that there's a, over here, let me try to sort of outline it without making too much of a mess. You see over here the beginning of a loon that goes in the front and then all the way around in the back to here, right? And also the other, the kind of twin loon is here, and then it comes around the back all the way and contains the other triangle. So note that the triangle is inside the loon. So this triangle is inside that loon. Let's call that, if this is angle alpha, this is the loon of angle alpha. Okay, that's one loon, one double loon. The other double loon, well, there's the beta one. So beta is this angle maybe, and you see that there's over here another loon that starts off this way that goes around and around, and the other side to the kind of antipodal point, the opposite point. And here's the other side of that loon over here, the double loon, and that comes back and swallows up the yellow triangle again. And finally, of course, for gamma over here, we get a third loon going this way and its twin going that way. I should change my color maybe to green. So now there's a loon that does this, it goes around, and there's a loon that does that, it goes around. So that means that that three loons cover the sphere, but each triangle is covered 3 times. What does that mean about the areas? So it means that the sum of the areas of the loons should be equal to the area of the whole sphere, but you have to add a couple of extra copies of each triangle because they got covered several times. And so let me write it carefully. The area of the alpha loon plus the area of the beta loon plus the area of the gamma loon must be equal to the area of the sphere plus a number of extra copies of the triangle. So how many copies of the triangle are there? Well, if you look at the front triangle over here, right, this an original triangle we were so interested in, it gets covered 3 times. One of the times was already taken care of when we took the area of the sphere. There are 2 extra times because because there were 3 times and one of them we already counted. So there's 2 left to count. And in the back, I get another copy that's counted 2 extra times. So altogether, I get 4 times the area of the triangle. Now we'll fill everything in. Let me write it carefully. So remember that the area of the alpha loon was 4 times alpha. So now we have 4 alpha plus 4 beta plus 4 gamma is equal to the area of the sphere, which was 4 pi, plus 4 times the area of the triangle. Let me just write it like that. And that's it. Now you divide by 4. Everything here is a multiple of 4. So divide by 4 and then subtract pi away from both sides, and you have the theorem that we wanted. So this proves our theorem, and we get to write QED. And that's the theorem. Let me add a little bonus fact. The bonus fact is that this is not just one-off, this theorem. It's not just one thing. It's a special case of a much more general theorem called the Gauss-Bonnet theorem. And I'm not going to tell you the Gauss-Bonnet theorem. You can look it up. It's fun. It's interesting. But one more special case of the Gauss-Bonnet theorem that's worth knowing is the case of triangles in the hyperbolic plane. And this is really my excuse for bringing in the hyperbolic plane, which is my favorite thing. The hyperbolic plane, this is a little MC Escher type picture, which you can, let me write MC Escher for one of the best places to look for beautiful pictures of some of these geometric objects. He was around for a number of years ago doing this. So this is a kind of map of the hyperbolic plane. I won't say anything about details except to say that the things that kind of look like circles here are indeed the straight lines of the hyperbolic plane. Some of them are actually straight line and some of them are kind of circular arcs. So here's a bunch of them. So these are, I hope you can see the red things I'm doing. And the triangles you see in this picture are the triangles of the hyperbolic plane. If you take kind of three of these sorts of lines, they come together and they fill up a kind of region, and that region is a triangle. And the theorem is, just like in the case of the sphere, that the sum of the angles of a triangle are not pi. They're less than pi now instead of bigger. They're less than pi. And the difference, now to get a difference, you should go the other way. You should take pi minus the sum of the angles. And that difference, once again, is exactly the area. And there's actually a proof of this, which is very similar to the proof I gave you for the sphere. All right, that's all for today. Thank you for listening. If you have anything else you'd like to comment or request any other math requests, please email me or leave comments below the video. And I hope to see you soon in person in Math Mornings. Thank you.